So today, the title of our paper is the Gaussian sketch for almost relative error kernel distance. My name is Wai-Ming Tai. This is a joint work with Jeff Phillips, who is my advisor. So here is some background. Suppose we have data from different sources. For example, we might have a geographical data. What we eventually have is a data set of two-dimensional points. More generally, the dataset we have is the points in d-dimensional Euclidean space. So after we have the data in the Euclidean space, we want to analyze our data by data analysis tools, such as principal component analysis, linear regression, linear classification, k-means clustering. We observe that all data analysis methods involve the Euclidean inner product. Then, what if we replace the Euclidean inner product by a kernel? But what is a kernel? So here are some examples. We have the polynomial kernel, which is defined as the inner product of xy plus c to the power c. Also, we have the Gaussian kernel, which is defined as exponential of negative norm of x minus y squared. And in this talk, we only focus on the Gaussian kernel. So now, let me introduce an important concept, and that is the reproducing kernel Hilbert space. Suppose we have a symmetric function, kxy. We call it a positive definite kernel if and only if, for any x1 to xn, in d-dimensional space, the matrix G is positive definite. Here, Gij is kxi xj. So now, let's consider this vector space. If we have a positive definite kernel, then there exists an inner product such that this equation holds. Also, there is a lifting map F such that kxy is the inner product of fx and fy. Finally, we can define this inner product space the reproducing kernel Hilbert space. So a side note here, the Gaussian kernel is a positive definite kernel. So now, back to our situation. Remember that we want to analyze our data in the Euclidean space. Then again, the question we have here is, what if we replace the Euclidean inner product by a positive definite kernel? Then the answer is, we actually analyze the data in the reproducing kernel Hilbert space. So we call that if we have 2 points xy in the Euclidean space, we can replace it by the inner product of fx and fy. And f here is the lifting map we defined before. But what if we have 2 point sets p, q in the Euclidean space? We can generalize it to the inner product of the average of fx, where x is over the set p, and the average of fy, where y is over the set q. We can expand this formula by the inner product equation, and it gives us this expression. Now, we define this as the similarity function, kappa pq. Now, we can define the kernel distance just like the Euclidean distance. As we all know that the Euclidean distance is defined as this. Now, we replace the Euclidean inner product by the similarity function. We define the square kernel distance as this, or the equation shown at the bottom line if we want to express it by the lifting map F. Then, why do we want to study the kernel distance? And there are some applications of it. First, we can use the kernel distance to do kernel two-sample test. That means when we have two distributions, we test whether these two distributions are same or how close they are. Also, we can use the kernel distance to perform locality-sensitive hashing on geometrical shape. That means we compare the shapes of geometric objects and see how close the shapes are. But now we have some challenge. As we can see in the definition of the kernel distance, we need to compute all possible pairs, kxy, and it takes quadratic time. Then here, what we want to ask is, can we do it better when we allow approximation? So in this equation, the right-hand side is the square kernel distance. And again, here, F is the lifting map. So one way we can tackle this problem is to construct a map F hat from d-dimensional space to row-dimensional space, such that the left-hand side of this equation approximates the right-hand side. Suppose we can do it. Then we can approximate the kernel distance in linear time. Here, let's define the problem more formally. We want to construct a map F hat such that we have 1 plus minus epsilon approximation of the kernel distance. And let t be the running time for computing F hat. Then, of course, we want to minimize the running time t. And note that we can always bring down rho to about 1 over epsilon square by standard JL lemma. So before we go into the technical details, we have some assumptions in our problem setting. First, we assume that our input point set PQ lies inside a bounded region of diameter L. For exposition, we assume L is constant here. Also, we assume that the squared kernel distance is at least alpha if P is not equal to Q. Now, let me introduce some previous results. Rahimi showed that we can construct the mapping F hat in d by epsilon square, alpha square time. They did it by random Fourier feature. Then Efron showed that we can construct the mapping F hat in d by epsilon square log n by alpha to the power d time. They modify the random Fourier feature. And finally, in the special case of P and Q being a single point, Chen showed that the construction time is d by epsilon square. Now, we can ask, can we further improve the result when d is small? Also, is the polynomial dependence of 1 over alpha necessary when d is large? So let's first consider a simple case when d is 1. Remember that the Gaussian kernel is a positive definite kernel. But why? So one way to show it is to expand the Gaussian kernel by the Taylor expansion. If we look at the expansion more closely, it is actually the sum of rank 1 positive definite matrix. So ideally, if we have an infinite dimensional vector Vx, which is defined as this. Then the Gaussian kernel is the inner product of Vx and Vy. By plugging it into the definition of the kernel distance, we have this equation. So basically, Vx could be the lifting map F. But we want a finite dimensional vector because we want to actually do the computation. So now, a simple solution here is we can take the first log 1 over epsilon alpha coordinates of Vx. But the running time would be log 1 over epsilon alpha. So what happens if we generalize it to the higher dimensional space? In d-dimensional space, the number of coordinates we need become 1 over epsilon alpha to the power d. If that is the case, then there is no significant improvement over the previous result in terms of 1 over alpha. And when we encounter this situation, the situation that the dimension or the number of coordinates is too large, a natural solution here is we can first apply dimensionality reduction, such as JL lemma. But the problem is still here, because we still need to scan through the entire input vector, which is the source of the problem. However, if we look at the input vector more carefully, we find that there is an underlying structure of the Kronecker product. Now, let me introduce a useful lemma. It says that we can construct a random hash function from n to the power k dimensional space to m dimensional space, such that the expectation of hx squared is norm x squared, and the radius of hx squared is epsilon squared by 10 times norm x to the power 4. Of course, we can compute hx fast. So basically, this lemma is Kant's sketch. But the only difference here is this lemma takes an input that has underlying structure of Kronecker product. So if we apply this lemma in our setting, we can construct our mapping in d squared by epsilon squared log d by epsilon plus d log d by alpha time. But what if the dimension d is really, really large? We can show that the number of coordinates we need becomes d to the power log 1 over alpha. So again, if we apply the previous lemma, we can construct our mapping in 1 over epsilon square log q 1 over alpha plus d log square 1 over alpha time. Now, this is linear of d. So let's conclude our paper. We want to compute the Gaussian kernel distance. And the approach is to embed the reproducing kernel Hilbert space into the Euclidean space for faster computation. So when the dimension d is small, the previous result is 1 over epsilon squared log n by alpha to the power d time. And our result is d squared by epsilon squared log d by epsilon plus d log d by alpha time. When the dimension d is large, the previous result is 1 over epsilon squared alpha squared time. And our result is 1 over epsilon squared log q 1 over alpha plus d log squared 1 over alpha time. Thank you.